Hello and welcome to C Programming 0 to Neural Networks, a brand new series on C programming here on the internet. As this is the first video in the series, I will do a brief introduction. So first of all, why 0 to neural networks? Well, I've scanned through a few of the available learning materials on C programming and other programming languages on the internet, and they all sort of take a very similar approach. Most of them read like a book, so it's like, this is an if statement, this is a for loop, this is a printf, and once you've gone through them all, you might know a fair bit about the language, but how to go from that to actually implementing anything of any complexity seems like a bit of a leap to me. So, although they are useful and certainly important, they don't really get to any kind of end goal. And then there's another kind of learning material which is usually pretty proficient programmers live streaming them making things, which is very interesting, but is a big step away from your basic C tutorial. So here we're going to try and forge out some kind of middle ground, a middle way, a middle path between those two approaches, and do a C tutorial with a destination in mind, with a target point in mind. And that target point is neural networks for a variety of reasons. I think a lot of people would like to learn how to program neural networks, and they're certainly fascinated and interested in it, and looking at all the crazy stuff going on in AI at the moment. It seems like a worthwhile endeavour, and for people looking for a job in computer programming, it's going to be a damn good thing to put on your CV if you say you can implement a neural network from scratch in C, isn't it? So that answers the first question of why 0 to neural networks. The second question is, why C programming? Of all the crazy languages out there in the world today, in the programming universe, why pick C of all the other languages? A 50-year-old language. There's lots of reasons, and most C series start with lots of good reasons to learn C, like it's really fast and it's close to the hardware, and you learn a lot about computers by programming in it, which are all very good reasons. But the best reason to learn C programming is that all the Jedi masters of the programming universe can program in C to a very high standard, can't they? To be a Jedi master of programming, you need to know C. You can be a genius, an absolute genius at JavaScript programming. You can be so good that you even get onto the Jedi Council, but you won't be granted the rank of Jedi Master, will you? And we all know how that story ends, don't we? You'll next thing you know, you'll be killing younglings in a temple and getting your legs cut off by Obi-Wan Kenobi. So if you don't want that to happen, let's crack on with learning C, shall we? Right, so shall we get on with part one? An introduction to part one, we're going to be doing the Hello World application, the de facto archetypal introduction to any programming language, a Hello World application. But what we're going to do is we're going to stop there, and we're going to explain as much as we can about that Hello World application before moving on. So let us begin our C programming adventure. Right, look at that bit of OBS magic. We switch scenes. So we've got the first. There's lots of challenges to learning any programming language. The problem is that the learning curve initially goes up like that. It goes up and then it levels out. Well, it goes up like that and it levels out, and then it goes up again and it levels out again, because you learn to, and it just carries on doing that forever. So it's a lifelong endeavour becoming a computer programmer if you're setting out to be a really good one. And that's what we're going to do here today. We're going to set out to be Jedi Masters of computer programming. So what I'm going to do, I'm typing into a terminal application here, and if you don't know anything about computers, anything about programming, that's fine, because I'm going to try and cover every single thing, even to excruciating detail. But to begin with, I'm just going to knock up a Hello World application, so we've got something, and I'm going to compile it, because C is a compiled language, and we'll cover what a compiled language is. Don't worry about that, we'll cover everything. But first of all, I'm just going to knock up a Hello World application, compile it, run it, and we can all look in amazement at the incredible results that it produces. So let's call our Hello World application hello.c. Very interesting name. First of all, we need to include the stdio.h, the standard input-output library. and then we need a main function, which is an entry point for our application, and we're going to return to the operating system a 0, and we're going to run one statement in our program, and we're going to run the printf statement, and in that we're going to put hello world, and that will do us. That is our first application. Held down the one key, and now we have a file, and we can cap that file and look at the contents of it, and there it is. That is our program, all saved by our text editor. We have a program called GCC. Now you can use a different C compiler if you would prefer. There is Clang, for example. Clang is another C compiler. I will be using GCC just out of habit, but apparently the Clang warnings and feedback you get is a little bit more understandable, a little bit more concise. So it's up to you. It doesn't really make any difference, but we'll be using GCC here in our Zero to Neural Networks tutorial. So, or series, I like calling it a series. GCC hello.c, bang. And now when we list, ls lists the contents of a directory, we've got two files. We've got a new file called a.out, which stands for assembly.out. And we can run that. It's lit up in green because it is a executable file, and when we run that, we print out hello world to our terminal application. So that's the hello world application. If you've attempted to learn C in the past, you probably would have got this far, and if this is all brand new to you, don't worry, we're going to cover everything. So, right, first of all, the first thing we need to cover is what is our environment. So if you've heard of JavaScript, which is a scripting language which exists in a web browser and makes web applications dynamic, well, turns websites into web applications, the environment of a JavaScript application is a web browser. So what's the environment of a C application? Well, you can set different target points, so it's not an easy question to answer. But we're going to be making user space applications, so it's a particular type of application, so we need to explain that. So we have a little paint program here, and we're going to need to draw an ellipse, and we're going to make me specify color green. What we're going to do is we're going to do an onion layer model of operating systems. This is a pretty standard way of explaining operating systems in an abstract way. So we're going to need an onion, and we're going to make our onion green. We're going to need a few layers to our onion. That will probably do us as an onion. The best picture of an onion you've ever seen, I'm sure. We're going to need a different colour for writing things in. And this smallest layer, the middle layer, the core of our onion, we're going to call the hardware. HW, hardware. So what's the hardware? The hardware is the physical computer. So if you're watching this video, the chances are you're watching it on a phone or a laptop or a desktop of some kind or a supercomputer, who knows. The point is that it first and foremost is made out of hardware. There's a CPU, a physical CPU, there's physical memory, there's a physical storage device in there, a physical screen, some kind of input, whether it's touching on the screen or a keyboard like I've got here on my laptop. All of that all together is the hardware. Now, our programs don't run directly on the hardware. We have something that's managing the hardware for us, and that something is called, you may have heard of this term before, it's called a kernel. K-E-R-N-E-L, kernel, not colonel, like in the military sense. A kernel like the inside of a seed, I think it is. You might have to look that up. So we have a kernel which manages the hardware, and we need a kernel to do that because if you think about the hardware, there's tons of it. You've got memory, which is broken up into bytes, which has got absolutely millions of bytes, and everything's happening at light speed of electricity. Us mere mortal humans can't interact with a computer at that level. We need to write a program to do that. So the first program that loads into memory when you switch on your computer and load it up is the kernel. And we need some way to communicate with the kernel, so around the kernel we have a sys call layer, a system call layer, syscall. And then finally, around the system call layer, we have the magical place where we're going to be making applications called, I've forgotten how to write words, user space, called the user space. So we're writing user space applications. Examples of user space applications are a web browser, a text editor, a terminal emulator, a file browser, a paint application, all kinds. Everything that you use when you're using an operating system. And if you're using your phone, exactly the same thing. All the things you press on there are user space applications. Now, so not all C programs are user space applications. We can do embedded programming in C, and we can target a platform like a chip that lives in a fridge and controls a fridge, and that's called embedded C programming. We're not going to be doing embedded C programming. We're not going to be building neural networks to run on fridges. We want our neural networks to run on our operating system. So, excusez-moi. We need to write user space applications, and just to get an understanding of this architecture and how our applications relate to this primordial stack. This is the lowest level stack that we're sort of dealing with. You've heard of the word stack in terms of like technology stacks. Well, this is the lowest level technology stack, and we're right down here with our C program. Fascinating place to be programmed. So let's say our user space application wants to access the Ethernet port, which is a physical hardware controlled by the kernel. So what we do is we set up some a software interface in our program called a socket. And we are going quite far ahead in our programming because we're on Hello World at the moment. But just to sort of get our heads around this relationship, we use the Ethernet port as an example. So we set up a software socket, and then we need to get access to the hardware and bind it to that bit of software we've written. So we send a request via the system call layer to the kernel to get access to that hardware device. The kernel will check it's available, check it's got an appropriate driver running it and all those kinds of things, and assuming everything's okay, it will send back to us a reference to read and write data to and from our Ethernet port. Now, Ethernet port is our network port, if you don't know what an Ethernet port is. And another example, let's do two examples. Let's say we want a big block of memory, a massive chunk of memory. What we do is make a request to the kernel for a big chunk of memory of, say 1,000 megabytes, and the kernel will check to see if there is enough available memory in the system, and assuming it is, it'll allocate that memory for us and send us back a reference to its location, so we can read and write data to that chunk of memory in our programs. So that's the relationship. This is the environment we're working in. So user space applications, terminal, web browser, text edit, all the things that we use, all the things that we're writing, and our C compiler as well. So let's get rid of that. We've done that. So let's go back to Hello World. Hello World. So let's explore what's just happened. So we've run our C compiler and we've outputted an a.out. So let's have a look at that file, shall we? a.out. The first thing we're going to notice is that it's not very readable. We have an elf here, which is not Santa's little helper. Strangely enough, it is a executable linkable format file. This is a sort of header to indicate what kind of file it is. And we can scroll along. We see there's just rows and rows of @ signs and XOR symbols, which is not very human readable. And that's because our a.out file is in a completely different language. It is in machine code. It is in a binary. So we have another type of editor we can open up called a hex editor, and I just so happen to have one installed on my computer called hexedit. And we can open up our file, and it's still not very readable, I will grant you that. But I'll describe this. So the left-hand column is an index. The three middle columns are hexadecimal representations of binary, and then the rightmost column with all the dots is an attempt at rendering any human readable bits in this program. And if we scroll down, we can't say very much about this at this stage, but if we scroll down, we'll notice that it just sort of goes on for ages. And there's a lot of zeros. There's a lot of zeros. Just nothing. 0, 0, 0, 0, 0, 0, and it carries on going and it carries on going. Well, I'm getting to a point with this, trust me, it's worth going through. Dot, 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 0, 0, 0, 0, 0. 45, 46, 47, 48. If you look at, there's a percentage at the bottom, the percentage of file we've scrolled down, And we get to this point and we can see our hello world. There's our text, finally something we can read. And then we can go down all the way to the end and there's more and more zeros. So the obvious thing to notice is that we have got a much bigger file. We can do ls-la, and our hello.c file was 77 bytes. And our a.out is 15,416 bytes. That's a lot bigger, isn't it? Yeah, something's happened. We can look at an intermediate stage. So our program is written in C source code, and the compiler converts our C source code into machine language. And it does that via converting, well, it doesn't really, but we can look at an intermediate step called assembly, where we can see a language closer to machine code. Our program converted to a language closer to machine code. We do gcc-S hello.c, and then we have a new file called hello.s, and here it is. And this is a lot less human readable. Now you can actually program in assembly. It's not a very enjoyable experience, but you can do it. It's possible to do. We have push HQ %RBP, and then we have some green stuff, and then we have movq %RSP, %RBP. You can imagine it's quite a challenge writing in this language, and this is why we developed C language, so we didn't have to write in that, strangely enough, back in the 70s. So we, the geniuses at Bell Laboratories. So our program starts off, we can think of it as our program starts off as what we write in C code, and then via this intermediate step of assembly becomes machine code, which the machine can write. Now, it's not just our program in this final outputted machine code that we can run on our system. The compilation process, it puts inside our program instructions to run the program, to create an environment for which it to run. It's quite a hard concept to imagine. If I introduce it now, early on, then we can build on this knowledge as we go along in our C series. So we end up with quite a sizable, we call it a binary file, and the a.out stands for assembly.out, and the assembly is this intermediate step called, well, at the moment called hello.s. Now, don't get overwhelmed by all this stuff. I'm deliberately just introducing tons of concepts before we move on, so that we can reference these concepts later and continue to use them and build on them. So I'm going to delete our a.out, I'm going to delete our hello.s, and rather than going too heavy into binaries and L files, just introducing that they exist and that there is a process of compiling our source code, our human readable source code, into binary language, into language that a computer can understand. And it's not just our source code that ends up in the executable binary, there's also instructions and lots of padding. All those zeros were padding, where things are spaced out and expected at certain points in our program for it to be loaded into memory, for it to execute. So it's quite a complicated thing, C programming, and this is why people find it quite a challenging language, because the environment is not just, like I say, a web browser, like with JavaScript. And the environment isn't, say with a Python program, isn't just an interpreter. We're running a program in an interpreter. A Python interpreter is written in C, so it's not that simple. If you described a Python environment in its entirety, it would be as complicated as describing a C program in its entirety. So let's go back to more simple things. So we're back to programming again. So we've got include stdio.h. What's this bit doing? What are we doing here? Well, we're including another file, part of the C standard library, and we can look at that file. It's in user/include/stdio.h, and it is a huge file. It is, I think, we go to the top. It's got lots of comments at the top. We'll explain comments later on. And it itself includes loads of things, bits and types, by the looks of it. And if we scroll down, let's just page down, go all the way to the end. 911 lines, and it includes loads of other things. But we have got our printf defined in here, which is what we're using. Now, you're not going to understand that. You wouldn't be expected to understand that at this stage, and you don't really need to be an effective C program. You just need to understand that you can include part of the C standard library and use functions in it. For now, that's all we need to know. And this gives us access to this printf function here, which outputs text to the standard output, and that standard output is trapped by our terminal application and displayed on the screen. And there's no easier way of explaining it than that. I can assure you of that, if you want the full and complete explanation. And this is why we're spending time going through a Hello World application. So int main is a function. Let's strip this program out and make the simplest program we can possibly compile. I reckon that'll compile, just main. Let's try hello.c. It gives us a warning, return type defaults to int. But we do get an a.out, and I think we can run it. And we don't even get an error, because the compiler is very clever and sorted out the problem. The problem was our main function needs to have a type, and that type needs to be a whole number type, and an int is a whole number type. And we return a 0. And we return a 0 to the operating system by convention. This is not something decided by the physics or the nature of the universe. It was decided that that was just the best number to pick to indicate that our program has finished successfully. So we can test that out. If we change that to a -1, compile our program and run it, we get a little X here, which is our terminal indicating to us that our program did not finish successfully. So by convention, we return a 0. Why a return? There's a lot of questions to answer to begin with. So every function returns, and to understand functions is what we're going to try and explain for the rest of this part of this video. So we're going to return to having our we still want to return to our hello world. So before we go any further, a main function, this word main, it was decided long ago in the late 70s that a main function will be called main. Not begin, not start, but main. Main function is an entry point to our application, our entry point. So it's the starting point where execution begins. So we can have tons of other things going on in our source code file that we compile. Our program always begins here at main. And we make main of type int and return a 0 by convention, so that the operating system knows our program exited successfully. If I do too deep an explanation at this stage, it'll just be too many words and too many concepts. If we just remember the right way to say things, that'll be a big help. So we can then use a printf function, which is another function inside our main function. And this takes a variety of arguments because it's a variadic function. And one of those arguments is, well, the first argument is a string, and that can say hello world. But we can also make our own functions. So we can have int hello. And we can once again return a 0. And we can put our hello in our main function. And instead of running the printf, we can just run hello. Let's say on this application we're going to be printing out hello world a lot, and we need to reuse that function, so we want to encapsulate it in our own function. We can now run this and we get the same result. We get hello world. So our program starts executing here in int main, and then runs our hello function, which is up here. Our hello function calls this printf function, which has hello world in it, and then it returns, and our execution returns to here, then gets to here, then the program finishes. Very difficult to explain, so we're going to do it with painting again. Great. Right. Diagrams, eh? Feels like being in school. So we need a stack. Shall we? Let's make our stack green. Let's make a stack green. So we have a stack, and then we have, I think we need it. We think we can do rectangles. I bet we can do, yeah, we can do rectangles. So we have 1, 2, 3. Can we actually write text? It doesn't actually. I prefer to write it out myself. Right, main. So we've got our main function. We've got our that we've just made a hello function, and we have our printf function. So what we're going to explain is how this program is ordered. So we're going to call this the stack, and this is the memory allocated to our program when the program is loaded into memory. We have a fixed amount of memory that our program is allocated, and the program begins executing at the main function. So the main function is loaded onto the stack main, and the execution begins at the top of the main function and then moves to the next line and the next line and the next line until we eventually get to return, and then we end our program. So the first statement that is encountered in the main function is the hello function. So the hello function is loaded onto the stack, HELLO. And in the hello function, we encounter the printf function as the first statement. So the printf statement is loaded onto the stack. And the printf function outputs to the standard out whatever we've got in our hello world text, and then the printf function is popped off the stack, and then we get to the end of our hello function because there's no other statements in it, just a return. So the hello function is popped off the stack, and then we get to the end of our main function, which is return 0, and the main function is popped off the stack, and the program ends. Our entire program lives in a stack of functions that we can call one function from another function to another function. Now, the idea of a function is a bit like a paragraph in a chapter, except it's non-linear because we can jump around, whereas a book reads. So it's probably not the best example, actually. There's no real good example. A function is a divider. We divide up our program into functions to make them easier to work with. So rather than having just a single main function with thousands of lines of code in, we break our main function up into sub-functions, and then we call them as and when we need them. So this is probably going to have all been a little bit daunting and probably not the best explanation to begin with, but there's no good place to start with learning a programming language. The best place to start is doing a Hello World application. The problem with doing that in C is that the environment is complex. And we're going to work on our understanding of the environment in the first few parts of this series. So take this part as just exposure to terms. Some of those words and some of those ideas will sink in, and if they don't on the first time, we're going to continually reuse those things and those ideas. So let's recap. So we have a C compiler, which we put an input file in it, and it will produce an a.out. The a.out file is a lot bigger than our source file, and there is an intermediate step of assembly language, which is a language closer to the hardware, which is a more machine readable. It's a less human readable but more machine readable, more machine sense making language. It's very difficult to write in assembly, so we write at this level in C, which allows us to, I wouldn't say write in a more human readable way, but a more human usable way. Our program is broken up into functions. We have a main function, which is a special kind of function. It denotes the starting point of our program. Our program begins at the main function. We can include parts of a library. In this case, the standard input-output of the C standard library. This allows us to use this printf function, which outputs to the screen. And that about does it. Oh, and we return it to the operating system, and by convention we return a 0 to indicate that our program has exited with success. That's the Hello World application. And the Hello World application runs in the user space on an operating system which has a kernel and a system call layer and manages the hardware. Lots of things to take in, lots of stuff to learn. Now, as I said, I'm going to reiterate this point again. Not all of that's going to go in. If this is the first time you've ever been exposed to C programming, that isn't all going to go in one go. But in time, it will. It will make sense. I will make sure of it. I'll make this a very worthwhile C series to sit through and to work through and to follow along. And by the end of it, these things will seem effortless, and we'll be building neural networks from scratch. Exciting stuff, eh? So stick with it. Right. I will look forward to seeing you in the next instalment of Zero to Neural Networks, C programming, Zero to Neural Networks. I think next we're going to be going through. I know exactly what we're going to be going through. I'll leave it as a surprise for when we get there. Have a nice, happy time programming, people. Enjoy your lives. Good day.